In the last video, I mentioned that these LC oscillations were analogous to a mass on a spring oscillating back and forth in space. Below is a graph of the electrical energy and the magnetic energy in this LC circuit. Notice that they're exactly opposite to each other at every point in time. Okay, this capital T is the time for one complete cycle. In other words, it's one period. And these two graphs are shifted by pi over 2. In other words, by 1/4 of a cycle. Okay, when one is maximum, the other is minimum, right? So now that we know the expressions for the charge and current as functions of time, let's see what these maximum values are, right? For both, I guess, electrical energy and magnetic energy. So electrical energy has the form of q squared over 2c, right? And really, this q is q as a function of time. Well, we found that from the previous video to be the initial charge times cosine omega t plus some phase constant phi. All right. Magnetic energy has the form of Li squared over 2. And remember, this I is effectively I as a function of time. So we also found that in the previous video, the form rather, and that's squared. So the current had the form of negative Q naught omega. Whoops. It's a weird omega. Omega sine. And that all was squared. And so this is ultimately of the form, well, that negative goes away. We have Q naught squared, we have omega squared, and we have sine squared. Can you see what's going to happen? And so if we take the total energy as the two of these added together, right, we have Q naught over 2c. Whoop, I forgot the squared. There it was. Plus, what do we have? L over 2, let's just leave it like this. L Q naught squared, omega squared. I forgot the cosine. Gosh darn it. We have there we go. Q naught squared times cosine squared over 2c. And we're adding that to L Q naught squared, omega squared, sine squared. Now we're going. All over 2. And cosine squared plus sine squared is just 1. If the prefactor, if the coefficient on both of them is the same. Right? That's how they cancel out. So let's see if that's the case. Let's see if this L Q naught squared omega squared over 2 is actually Q naught squared over 2c. Well, we know what omega is. Omega is 1 over root LC, so that's squared. So that means that we have a factor of 1 over L times L, right? So our L's go away, right? And we have indeed Q naught squared over 2c. So that's the same as that. We are good. Thus, the maximum energy in the electrical regime, right? The maximum electrical energy is that. We see that right there. And it's also the same as the magnetic energy. That. Same thing. So regardless of if you have the blue or the green graph, they're always going to have the maximum energy at any point in time. Thus, that means that they have the total energy and it's conserved for all time. They just change back and forth, going from magnetic to electric. And down here in this table, it's again, this is analogous to a mass on a spring, whereas the potential energy for a mass spring system was all in the spring, and the kinetic energy, right, was all in the, well, the block, right, the moving block. In an LC oscillator, the potential energy is in the capacitor, and that's analogous to the electrical energy, right? That generates the potential difference to push the charges around the circuit. And when those charges are actually moving, we have a current, and that's analogous to the kinetic energy, right, for the inductor. So that's kind of the analogy to 4A, but now in 4B for an LC circuit. Thanks for watching.